So far, we have seen DFAs, deterministic finite automata, and we know also how to obtain a DFA out of a non-deterministic finite automaton, and usually we can convert always this to a DFA. And also we have seen that an NFA with epsilon transitions can be converted into an NFA without epsilon transitions. And usually this is obtained whenever we have a regular expression, right? So we know this process already, that this is what we have been doing the last exercises. And also we know how to obtain a regular expression out of a DFA. So we have no problem with this. And now we will see that there is another way of expressing a DFA, which are regular grammars. A regular grammar is a rewriting rules grammar, because we have a rule that states a symbol, and then we have an arrow, and then it says that, what can be written instead of this symbol. For example, A or AB or something like that. Usually our rules will be written in this way. We have one left side, one arrow, and then one right side. Particularly, regular grammars have some restrictions. Particularly, the left side will be always a non-terminal symbol. We will classify symbols in two kinds. We will have terminal symbols, which correspond to those of the alphabet, which are, for example, A or B in our examples, or non-terminal. And this will correspond to states of the automata. There will not be always a direct correspondence between these states and the non-terminals. Oh, my screen is not...
Professor Aram, I'm sorry to interrupt you again, but Dima cannot connect.
Okay, yes, don't worry. Let me see what's happening with him. I don't have him in the waiting room. I don't know. Does he have this link?
Yes, he said it's not working. I don't know why.
Yeah, because I have disabled the waiting room, so I don't know what can be happening.
Maybe the password again, we can send him.
Yes, tell him to try to use this link, please.
Thank you.
Well, let's continue. I hope he can connect. Maybe it's a proxy issue. Okay, so we are all here. And I was telling you that we will see today grammars, and particularly regular grammars. And usually we'll be using a non-terminal followed by a string of terminals or non-terminals. So in order to show you how a grammar works, let me write a short grammar, or maybe it's easier if I just copy it from the book instead of writing it all again. So this is grammar shown in page 50. And usually the beginning of any grammar will be an S. I have used S here, and in our example, we could replace this sentence by an S. In general, also in this example, the non-terminals are shown by brackets. So all these that I am highlighting are non-terminals. Non-terminal, non-terminal, non-terminal. And you can see in this case that John and Mary are terminals. So everything that is inside triangular brackets will be a non-terminal for this example. So what this example does is to allow us to create new sentences. Let me copy this into a new page so that we can play with it a little bit. It's exactly the same, just we need more space. So we will begin with S, or with sentence, and you will see why this is called also rewriting rules. We have here sentence, and then this sentence can be rewritten in only one way. If we look at this sentence, at this rule, we can see that sentence can be rewritten as subject, predicate, period. Then, in turn, each one of these elements can be rewritten in a different way. For example, subject, we have only one rule for subject, and it says rewrite subject with noun. If we rewrite it, we can write everything as noun, and the remaining part goes exactly the same, predicate and period. So you can see we are only modifying this part, subject. Then we have two options. If we want to modify or to rewrite noun, we have two options. We have noun can be John or noun can be Mary. Let's choose one randomly. So let's say John. John, and then continue the remaining parts, predicate, and then period. Now we have to rewrite predicate. If we rewrite predicate, we have two options, intransitive verb and transitive verb plus object. So I think with this, everyone can remember the difference between a transitive and an intransitive verb. So who wants to explain that to me, please? What is the difference between an intransitive verb and a transitive verb? We have also that in Spanish, verbos transitivos and intransitivos. But particularly we learn it when we are learning English. You have a hint here, because you can observe something that the transitive verb is taking and the intransitive verb is not. So that is the difference. I just want you to tell me that. I know you have it at the tip of the tongue, but maybe long holidays have eaten your tongue like a mouse.
I have no idea.
I think a transitive verb is when there is an object that receives the action, and an intransitive verb is when there is no object that receives the action. I think.
Right. That's the definition. For example, rain. If you ask who is receiving the action of rain, well, maybe the earth or something, but you never say You never state it. You just say it, the subject, rains. And when you have a transitive verb, you need to specify an object. For example, give. Someone gives something, and this is the direct object, to someone, and this is the indirect object. Yes. So in this case, we don't care about indirect objects. We just care about direct objects, and direct objects are marked only by object in this case. So yeah, Christian is correct because he says a transitive verb needs an object and an intransitive verb does not need an object. And this is written here in these two grammar rules. Of course, this is a very simple grammar and it has two predicates, two kinds of predicate. One is just an intransitive verb, just as rain, and the other one is a transitive verb. And we will see what kind of transitive verbs we can have. We have two examples here, hit and likes. We will go to that part. So let's rewrite our predicate as a transitive verb, just to have more fun. So John, and then a transitive verb followed by an object, and then again the period. Observe that the part that I am changing is only the one that is highlighted. So the predicate becomes transitive verb and object, just as this rule says. So it's very easy. I'm just rewriting the previous part, or the part of the sentence. I'm rewriting it as according to these rules. Okay, now we will continue this process. I am taking always the leftmost part. And why I'm not taking John? Because John is a terminal symbol. Once I have reached John, there is nothing I can rewrite John with. So John is a terminal symbol. So the next non-terminal symbol is transitive verb, and now I will rewrite transitive verb with one of these two options, hit or likes. So which one do you want?
Hit.
Hits.
Hit.
Okay. Hit. Okay. Actually, it should be hits. You're right.
Yeah, hits.
So the English version has also these errors. The Spanish version has the same mistake. So now I see it comes from the English version. Okay, so it hits. If we choose this one, we can say John hits, and then we still have the object and then a period, right? Okay. We continue this process now with object, and we have only one option for object, only one rule. So we take this one, John hits, rewrite object as noun, and rewrite period again. And if we want to see what is a noun, well, we have only two different nouns here, here and here. So noun can be John or Mary. So just for fun, let's say Mary, because John hits himself is not so fun. Well, it's not disclaimer. In any way, it is fun just to hit someone. Just we are playing, okay? So John hits Mary, and then period. Okay, so period at the end just is rewritten as a period, surprisingly. Mary, and voila, that's it. There are no more things to do here. Why? Because once we have reached all non-terminal symbols, there is nothing I can rewrite. So it's finished. So we have started with sentence, and then rewriting each one of its elements, we have reached a sentence with terminal symbols. This is how we will be using our grammars. Grammars can be generative whenever we use them in this way, or they can be used for recognizing if a sentence is correct or not, or we can say that this sentence is recognized by this grammar or not. So we will write here generation, because we are generating a sentence or recognizing. Recognition. It's exactly the same, just what changes is the order of rules being applied. So for example, I can ask you, in order to recognize, if you think that John, no, now the revenge, Mary hits John, period. I can ask you, do you think this sentence can be recognized by this grammar? And then what we will do is exactly the reverse process. Now we can say, okay, Mary is a noun. And we can do each one separately. Now, we know that this is a noun, and that noun in, well, let's continue. Noun, and now hits is a transitive verb. And we know that John is a noun. Sorry. Okay. Oh, it got erased. Okay, so let's start again. Sorry. Mary is a noun. Let's do all of them in a single iteration. Hits is a transitive verb. And noun, and John is a noun. And finally, this is a period. So you can see Mary, I know is a noun because I'm just following the arrow the reverse way. Hits, I know that hits is a transitive verb following the arrow the reverse way. John, I know that John is a noun. And finally, I know that this period is period by following this the reverse way. Now that we have this, then I will try to get to sentence again.
Professor, I think the translation got interrupted or something.
Yes, I'm trying to reestablish it. And it says, wait. Let's try again. That's it. Okay. So we know Mary is a noun, hits is a transitive verb, and John is a noun, and this is period. Okay. So now we will continue so that we will try to reach sentence. So this noun can be a subject, right? I will rewrite this noun here as a subject. The transitive verb needs an object, so I will leave this untouched. But I will make this noun here an object. Why? Because I can use this rule backwards. Noun is an object. So now this will be object. And period is the same. I will just write P. Now that we have this pattern, transitive verb and object, I can make this a predicate. A transitive verb followed by an object is a predicate. So I will rewrite this as subject, predicate, and period. And if we have subject, predicate, and period, then we have a sentence. And with this, we know that this sentence is recognized by this grammar. Mary hits John is recognized by this grammar, or we can say also that it, some people say it's grammatically correct, just because there is a grammar that is able to recognize this. So we have, yes, Dima?
I wanted to ask, like, and how do we know that we can see the noun as the subject or an object?
Yes, good question, because in this case, we know that we need a subject here and that we need the object afterwards. If for some reason, because what you are saying is, let me change color, you are saying here, when we have noun, transitive verb, noun, why not I say this is an object, and then transitive verb, and then subject, and then period, right? We can do this. And of course, it's completely valid because every noun can be an object or a subject. However, if we do the green path in this way, then we won't be able to use transitive verb subject because there is no rule that allows me to reach a predicate. So in this case, I won't be able to reach sentence. This is very similar to the process we did with non-deterministic finite automata. Because do you remember that there were many different ways to recognize or to read a symbol? And as long as there was just one way of accepting a string, then we can say the string can be accepted. Here, of course, the same, because there are many, many ways of not accepting a sentence. But if there is at least one combination that allows me to reach sentence, then I can say the sentence is recognized by this grammar. If I do this, then just I want to reach sentence at the end. So I need to examine all different possibilities, which for this grammar, there are not so many, but for more complex grammars, we have the problem that it can be exponentially growing number, and it can be very, very difficult to parse it. That's why we will also see ways of optimizing these parsings. Whenever you define, this is for natural language, but this will also work for formal languages. So the important thing in formal languages is that these compilations should be done very optimizedly. It's very optimized because we can have programs with lines and thousands of lines, and this will be used also for compilation. So that's why last class, or maybe one before last class, I was talking to you about very old computers, so that you can have a little bit of this grasp or feeling of limitation of memory, limitation of speed, limitation of, in general, for all the algorithms. And it is not that nowadays we don't have limitations, but we are not so used to feeling that limitation. We can say, you can just reserve 1 GB of memory. Yeah, we have more and more, don't worry. But for all processes that have a very large number of lines, we need to take care of these kind of things. And maybe we don't care so much nowadays because most operating systems are already done. However, they rely on techniques like these ones. So yes, the question, just to close the question, was why didn't we choose noun as an object? We can, but we want to reach sentence at the end. And we want to reach, or we are seeking to reach sentence at the end. We will see this phenomenon several times when trying to recognize a string if it belongs to a language. Okay, so we have seen now a way of doing generation of sentences or recognition of sentences. Yes, and just to be just to be a little bit exhaustive, let's generate the remaining things we can generate with this grammar. I will make this part small. So that we have space here. So beginning with sentence, we can choose John likes Mary. Mary likes John. Mary skates and John skates. John hits Mary and Mary hits John. So this is a short story. It's a kind of a love story because John likes Mary, then Mary likes John, until they go skating together, but then they start hitting each other. Of course, not purposefully, but afterwards they don't like each other anymore. So sad. Just an example of sentences that can be generated with this grammar. So you can see a whole story included in this grammar. However, there are also other examples that can be generated, other sentences that can be generated that were not included in this story. For example, what if John likes John? He likes himself. Or maybe he likes another John. We don't know. Or Mary, I'm sorry, I have a phone call. I don't know who is it. Bueno. They just hung up. I don't know what do they want. Sorry. And Mary likes Mary. Or even they start hitting themselves. Of course, each one of them with their corresponding period. Yes, so now we have this list complete. Maybe you can examine this. Let me know if you find another sentence that can be generated. Please check it.
Doesn't look like it.
I think these are all the sentences, right? That can be generated from this grammar. So also you can see that this grammar is generating a language, and the language is, as always, the set of all different strings that can be generated within it. So this is a language, and if we say this is grammar GMG, Mary and John, then we can say that this is the language of grammar Mary and John. So this is a set. In this case, this is a finite set. And do you remember what can we say about finite languages? If we have a language and the language is finite, then this language, what kind of language is this?
It's regular.
Right. Remember that if a language is finite, then it's regular. However, we cannot say the contrary. There are some languages that are regular and they are not finite. Yes. just to recall that. So we are defining with this grammar a regular language, which in this case is very short, is kind of simple, but we can see other examples. Any question here? Okay. So I want to connect the idea of grammars with finite automata. Let's rewrite this grammar in a simpler way. For example, let's say for each S, this will be S, this will be U, this will be P, and this will be D of dot of period. Subject is U, noun will be N, and John will be just a J. Noun M. Predicate, this will be an intransitive, no, that's right. Verb and subscript I. It will be verb and subscript T. Object, predicate, this is VI, and this will be S, lowercase. VT is H, VT is L, and this is O, N, and it will be P and the period. So why do I do this? You will see. I will rewrite this grammar using these new symbols. S, U, P, D. U can be written as N. N is John. Noun is Mary. Predicate is an intransitive verb. Predicate is a transitive verb followed by an object. And then an intransitive verb is skates. Transitive verb is hit. Transitive verb is likes. And O is a noun. And finally, P is a period. So this looks more like regular grammar. Remember that capital letters are non-terminal symbols and that lowercase letters are terminal symbols. If I highlight them, all these are.
Professor?
Yes.
Sorry for the interrupt. So I guess that the last sentence or the last letter is incorrect.
P?
I think there is
yes.
period. The P?
Yes. Very good.
Is D.
Thank you very much. Yes, very good. Otherwise, it won't work. I'm changing the language. Thank you very much. And the terminal symbols are all of these ones. So remember, non-terminal symbols and terminal. You will need to recognize them always in your grammar. And as I said before, in this case, non-terminal symbols are written with triangular brackets, so it's exactly the same. We are just doing an equivalence. There are two ways of showing terminal and non-terminal symbols. So from now on, in our automata, we will be using this notation. Capital letters for non-terminal and lowercase letter for terminal symbols. Remember that terminal symbols are those that cannot be rewritten because in order to rewrite a symbol, it needs to be a non-terminal symbol. And also pay attention here that these I and T are just part of this symbol. It's the same. It's just as if this will be one letter. Just this is a subscript. Don't be confused by that. Okay, now that we have this, I will show you how to convert this grammar in order to obtain a DFA. in order to do this, we need to change our rules in a specified format. And this format should be always a non-terminal symbol at the left, followed by a terminal symbol, and then a non-terminal symbol again. Let's say here, let me change this. So M and N are any non-terminal symbols. So what we have here is a way of writing these rules, and all rules should be only of this kind or this kind. We can say that this is the canonical way to write a grammar. So in order to convert this grammar into a canonical way, we need to do some substitutions. First, we need to identify all rules that do not comply with this. I think all of them do not comply. So in this case, we have UPD. We need to substitute this U. Let me show you how. We have UPD. This rule, which is the first one, we will try to convert this one into a canonical rule or a set of canonical rules. We can see here that the first U is not a terminal. So in order to look for a terminal, we will substitute this U by all of its variations. In this case, we have only one variation. So we will substitute U with N. So we will rewrite this rule as SNPD. Still, we don't have the canonical way. So now we will look for this. We can erase this one because we have rewritten it. We see that this N can be rewritten as J or M. So we have S, J, PD, or S, M, PD. Yes. So we are a bit closer of this format. Now what we need to do is, whenever we have two non-terminal symbols grouped together, such as PD, we need to create a new non-terminal symbol that can be named X. So we will X, which will be PD. X1 is PD. Now, if I rewrite this as SJX1, SMX1, why X1? Because X1 is PD, and this is PD. It's exactly the same. So this PD becomes X1, and we can see that this complies with this format. So the first rule is already converted. Our rules are those that are marked with blue. Now, we will go with this one. However, we can see that this U is used only by this rule. And this rule is already converted, and this is not using this U anymore. So we can skip this rule. The same in this case for N, because there is no N using these rules. So we go with P, and P says that it should be written by VI. And in this case, we will rewrite this as this P needs to be rewritten as S. So whenever we have P, we can rewrite as S. For this rule, P can be rewritten as S or P can be rewritten as VTO. So VT can be H or L. So if we rewrite this rule, we can make P H O or P L O. And both of these rules comply with this one. Why I'm doing this? Because if we check this part, P, VTO, and I am substituting this with H and L, then I reach these rules. I do this because I want to have all rules like this one. Okay, and finally, this O is an N, and N is J or M. Whenever we have all these rules that are alone, for example, we have O. I'm doing this like very quickly. Don't worry if you don't get it now. I'm just, this is just the introductory part for this method. So I will give you the method more slowly afterwards. So this O that can be rewritten as N, we have this N that can be J, or that can be, this O can be J, or this O can be M. For these rules that have nothing here, we can try to add something here. Something is empty. And what we will add here is a new rule, for example, L. And this L, new rule, will be a lambda rule, which complies with this one. So why am I adding this lambda rule? Because this symbol was alone. And if I substitute it by an L, and an L is this way, then I'm able to add it whenever I want. Okay, so we are almost finishing. Finally, we have this rule that we created before here, and we need to convert again this PD. In order to convert that PD, we need to expand again this P into VI or VTO. So if we replace this P with VI, the first one, X1, PD, the first one can be X1 is VI, O, or the next one, let me move this, or X1 VTOD. We can write that. Again, I substitute VI by S, I have X1 SO, and this is done. And finally, for this one, we will do the same again. We have here two non-terminal letters, O and D, and I will rewrite that as X2. This will be X2. So I add another rule, which will be OD, and finally, I will write this as X1 H X2 or X1 L X2, which comply with this one. So what we are doing here is I am trying to obtain always a non-terminal symbol here, followed by a terminal symbol. After this, you will do this with a much more simpler grammar, so that you can do it by yourselves. This is a bit complex example, maybe not not so good to start with. I'm sorry, but I want you to see what happens with this. And we are about to finish. So now we have another problem. Why? Because in this case, we have fixed X1, but now we have another problem. We have the problem of what happens with X2. X2 is not again in the format. So we will work here with x2, which is OD. So I will substitute O by N. Now I have ND, and N can be only J or M. X2, M, J, or X2, M, D. And that's it. Now we have these two rules that comply with this format. Now there is only one last, which is this D. Remember what happened when we have a symbol by its own, we can add this one. So we will rewrite this last one as D dot L. And now it complies. Why? Because it's a terminal followed by a non-terminal. And this is it. We have converted this grammar into a canonical way. This will help us. I will erase this one. With this, we can do the following, and that's what I want to show you. We have, starting with S, we will take this, and this will be our starting symbol. So we have start, and we will draw it as a symbol. And by using our newly created rules, we will say we have JX1 or MX1. So this is X1, and we have J, and we have M. Yes. And for X1, now we have S. Sorry, this is not O, because X1 is only is D from dot. My mistake here. SD. So we have from here, we have S, D. Yes. Or we have from X1, HX2 or LX2. H, X1, sorry, X2, or L, X2. And from X2 is here, we have J or M and then D. J or M. And finally, this one, this DL, says that there is a dot and then an L. And finally, all those rules that end in lambda are accept states. And that's it. So what happens here? We have our grammar converted into an DFA. We have John skates, dot, finish. Mary skates, dot, finish. Or we have John likes Mary, dot, finish. John likes, okay, the same. There should be also John likes John here. This is missing, and this is missing here as well. So we have John hits Mary, or John hits John. John likes John. John likes Mary. And Mary hits Mary. Mary hits John. Mary likes John, or Mary likes Mary, and finish, which are the same sentences that we had before. So this is a bad example, bad because it's very complex. Sorry to trouble you, but this is an example on how we can convert a grammar into a DFA. There is always a way to convert a grammar to a DFA as long as this grammar is regular. As this is a regular grammar, then we have a DFA. If the grammar is not regular, then we cannot convert it to a DFA. Okay, so, well, this was the most difficult part. Now let's go to easier parts. So don't worry. Okay, so far you have seen, like, I don't know exactly how teacher did some strange rules, applied some conversions, and obtained a DFA. Okay, if you have it like a fuzzy learning state, it's okay, don't worry. Yes, the explanation was not so clear. So if you didn't grasp it, don't worry, it's not your fault, it's the teacher's fault. Christian.
Yes, we can join the two states X2 or?
Oh, yes, that's why I needed, yes. Sorry, very good. That's why I needed M and J separately and add more things. Yes. I should have done that. So we have X2, and then we have M, and then we have J, and it's much more easier and clearer, right? Thank you, Christian. Okay, so far you are detecting things like this, and this is very good. So let me do the reverse process. Let's suppose we have, now you can forget about John and Mary for a while. Let's suppose we have an automaton like this one. We have S, X, X, Y, Y, X, and Y. If I told you extract the regular grammar out of this automaton, do you think you can do it?
What do I need to extract again?
The grammar.
The grammar.
The grammar.
In which the grammar?
Remember that what we did before was the reverse process. So in the reverse process, we to convert rules into a way that was suitable for obtaining something like this. Here, I will show you this is very straightforward. We start with S, and then we follow with X. Where do we go? We go to X uppercase. X takes me to X. Then, also from S, we go to Y. From S, we go to Y. And also, being in Y, if we have an X, we go to X. If we have an X, we go to X. And if I am at X with a Y, we go to Y. And finally, for showing the accept states, we add rules with our lambda rules. You see? So this is much more easier. Now I will ask you to do some exercise. So now please write the grammar for this one. Okay, have you finished? Can you show me your answers, please? Okay, yes, A. Okay, you did it with A and B. Okay, yes. There was Sarah. Okay, Christian. Oksana. Okay. And Abraham has raised his hand. I don't know if you have any question, Abraham. Emilio, okay.
I have a question. Sure.
Okay, Maraya, please go ahead with your question.
Camilo.
Camilo, yes.
It's necessary to write the pit one or?
The pit? No, only as you did, only the rules. Cesar, it's okay. Thank you.
The last state is a pit, so we need to write, or
Well,
it's not necessary?
Well, you are not sure if it's a pit. If you assume that all the symbols are X, are A and B, then yes, it's a pit. However, the language, the alphabet is not explicitly stated. So if we assume that A, B, yes.
Okay.
And well, I see your question. If this holds, then this is a pit, right? And if you erase this, and this, the behavior of the automaton should be the same. That's your question, right? So it should be something like this, B, and then B. And if anything else comes, or anything different comes afterwards, it will go to a pit. Then the interesting part is, well, what if we write this as a rule? What will happen as a grammar? Sorry. So let's say S, X, and Y, just to mix. Some of you used A, B, and C, and some of you used X, Y. Just please observe that this should be always S. Regardless of this is X, Y, or anything, this should be always S. So you can write XAX or SBY, XBX, and YAY. And the accept states X and Y. Right? So I saw very quickly, if you added another accept state, is not correct. And then the question, let's try to see what happens. Suppose that we have an invalid string, like for example, A, B, B, A. This should not be accepted, right? Because we have A, B, B, and then A. So the same here, A, B, B, and then we know it goes to the pit. What happens with this grammar? We have A, B, B, A. So A, B, B, A, we start trying to parse it. We have, this is not so easy, but let's try to do it. We have this last lambda here. Wait. Okay, then with this lambda, now we can, this A lambda, we can convert this lambda to Y. So we have A, B, B, A, Y. Then this AY is converted to A, B, B, Y. And then we have BY here. This BY gets converted to S, A, B, S. And then we cannot do anything else from there. So maybe if we try different ways of accepting this, it won't be accepted. There is no way to obtain S out of this one. despite we have not included the pit. So the question we have is very interesting because Camilo decided to remove the pit, and then the grammar is equivalent in this case. Well, in all cases, if you recognize something that is a pit, and it will be a pit whenever your alphabet corresponds to all symbols coming in and coming out from this state, that should be the definition of pit. A pit is that state that has arcs coming into it corresponding to every symbol in the alphabet, and also every arc coming out of it and coming back to it are all the symbols in the alphabet. So this is a pit, yeah. I hadn't recognized it as a pit, but yes, this is a pit. If we consider this, let's suppose yes. If we remove it and then obtain the grammar, then this would be exactly the same behavior as this one. So you could have removed it. Yes, so this is for answering this question. So if you don't remove the pit in your exercises and obtain the whole grammar, adding the arcs for this one, so if you added, for example, Z, and then also you have this, and then you need to add from X with A, go to C, from Y with B, go to C, and from Z and A, go to Z, and from Z and B, go to Z. So you can see that if you add these rules, the grammar does not change. So maybe you can think of these rules as redundant. However, both grammars, this and this with this one, are called equivalent grammars. So there is no single grammar corresponding to a language. To a single language, there are an infinite number of possible grammars. And we know that this is infinite because you can keep adding here more. For example, if you add F, A, F, G, A, G, H, A, H, you see that these are not useful. However, you can add them to the grammar always. And again, if you consider all rules, they make a new grammar. Yes, are you understanding this point?
So how are they called? These grammars that have the same language?
Equivalent grammars.
Equivalent. Thank you.
Okay, so if you didn't remove the pit, don't worry. This is like an extra, or like thinking or asking, what happens if I remove the pit and then I don't add these rules? Well, that's okay. But the normal procedure is very simple. Just what you did is okay. You only need to select each one of these and add their corresponding rule, and do not forget the accept state, the lambda rules. Yes? So up to this point, you can see this is very straightforward. Now, another exercise for you. An easy one is this one. Now the reverse. Your goal is to draw a DFA or an NFA from these rules. Okay, Cesar. S, X, X, yes, yes. And Y. Okay, you just the lower part of Y is missing a symbol. The arc of Y is missing the symbol.
Yes.
Cesar. Maraya, okay, okay, okay. Very good, Maraya. Sarah, just make it a little bit okay. Okay, very good. Oksana, right. Christian, right. Emilio, very good. Christian, show me again, please, because I wasn't able to see. Okay, very good. Abraham, okay. And Oscar, okay. Erika, cannot see. Okay, 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 very good. Arturo, okay. Nice. So you can see this is this was easy. So maybe you are wondering, well, why the first one was so difficult? Well, because sometimes things are written as this. For example, X, A, B. A is Y and B is Z. So this is not in the canonical form. So what we did with the first exercise was to apply different mechanisms. The first one was when you have two non-terminal symbols, then you create a new one. And usually you can name it X1 or X2 or XN. You add this to the grammar, X1, you delete this rule, and then rewrite it with this new symbol. Oh, sorry, this is wrong. You rewrite X1 as AB, and then you rewrite S as X, X1. Yes? So you take a pair, you have X1 goes to AB, X1 goes to AB, delete this rule, and then rewrite S, X, X1 with the new one. And now we have another problem. This kind of problems is when you don't have the first one as a terminal. So in order to obtain a terminal here, then you do the following. This A, you substitute it by the corresponding terminal. In this case, we are lucky because we just rewrite this as Y, and then we delete this rule, and we have X1, Y, B. And then this complies, and this complies. And the third thing you do when you have things like this is that you need to add something which is missing, which is the another state, because there is nothing else than this. The new state you will add is L, and L is lambda. Of course, whenever L is not used previously, because maybe you have already an L, so you cannot reuse L. You can do L1 or another letter. And now you can see this complies, and this complies. And now you can simply draw S, X, X1, X1, Y, B, and B is Z, L, and L is an accept state. If you examine the old one, X, A, B, A is Y, and B is Z, you can see it was X, Y, C. Just like this one, X, Y, C. So we have done, again, three things. One, for two pairs of non-terminal together, like M and N, then you can create a rule which is X1 M N. We did it here. The second thing we did was whenever we have, or if we have MN for in some rule, X, MN, and then M is a terminal, just substitute this M, this T, substitute here, so that you have X, T, N. And the third mechanism we have is whenever you have something like M, T, then you just add L, and then L goes to lambda. So these three mechanisms you will be using, but there is no exact way of using them. There is no order. They say 1, 2, 3, but sometimes you need to apply first number 2, and then number 1, and then number 3, etc. You have to try if they yield you to this, if you are able to obtain rules in the canonical way. Yes, that was what we did in the first example. We applied these three mechanisms in different orders until we obtained our result. So now you will try with a more difficult example. And a fourth mechanism, sorry, there is a fourth one. Let's suppose you have something like M and you have T, U, and M, for example. Then what you will do here is you need a non-terminal here. So you will change T by a uppercase and then substitute or add this rule here. And of course, afterwards, probably you will have to add this as well, but don't do it right now. Just leave it for the end. So you can deal now with two non-terminals together, with two terminals together, with no non-terminal, and also with a rule that starts with no terminal. Remember that all rules should start their right side with a terminal. Yes, like this, and this. Okay, now that you have these rules clear, please try this exercise. Sorry, not yet.
Teacher.
Yes.
I have a question about what happened with the A, because it says that A goes to L with Y.
Oh,
So
yes, this one.
there are
Yes.
missing.
Good question. We can draw it. It says A goes with a Y to L. Here it is. And I didn't draw it because there is no way you cannot get into A, as you can see. But if you want to draw it, you can. It's like this, but there are no arcs coming into it. And of course, this is a valid DFA, but you can have as many states that are not used. As the same as in the previous grammar, I could add an infinite number, well, not infinite because it should be finite states, but I can do this infinitely. We can do H with a Y, or J with a Y, or K with a Y. You see, we can continue adding more and more states, and just they won't be used, but they are valid. They are just kind of orphan. There's no way of reaching them.
Okay, thank you.
Yes, but that question is also a very good one. Thank you for your very good questions and for your attention. I see that you are grasping it properly. So please try to do this one. You will need to use several of these mechanisms, and you need to rewrite each one of your rules. Start one by one and try to derive the correct ones for the first one, and then for the second one, and then for the third one, etc. Also, let me remind you of something which is very important. If you try, for example, and you say, here, I need this to be uppercase, and then you change this X, this S for X, Y, X, something like this. So when you are using this in uppercase, please be aware that this Y should not be used, should not be already used, because otherwise you create a clash of symbols, meaning that the symbols are already used for something different. So every time you introduce a change like this, make sure that the symbol is not in use already.
I have a question, teacher.
Yes.
In the second rule, when we rewrite,
Yeah.
the M disappear?
Yes. Maybe it's better. Yeah, because you are rewriting this, because you can substitute this M with a T, then here M can be substituted with T, yielding X produces Tn. So yes, it disappears. Also, be aware that this works whenever M is substituted only by T. If you have another thing here, like M also produces, let's say, U, then you need to write both ones, X Tn and X Un. Why? Because you have these two rules. Substitute them here and here, then you will have two rules, this and this. Oscar, please go ahead. A little bit lower. Okay. I think it's okay. I cannot see very well because it's like very, I mean, it's too, okay. No, yes, there. Let me copy. Wait a minute. Okay, let me check it. Because I'm not sure if I can see very well. Give me a second. I think it's a little bit more. Oh no, let me see. Wait. Yes, it's okay. Thank you, Oscar. Maraya? A little bit lower, please. Okay. Yes, good. Oksana. Give me a second, Sarah. I think, sorry, I didn't see your hand. Let me check Oksana. X, Y, X. There is a small problem, Oksana. Please check the loop of the X. Sarah, X, Y. Yes, very good. Very good, Sarah. Thank you. Christian, X, Y. Oh, it moved. X, X, Y. Good. Yes. Sorry, Christian. There was something erased over there. Can you show me again? But maybe. But that's erased, right? The Z and that I just ignore it.
Yes, I think it's the other side of the.
Ah, okay. Thank you. Christian, X, Y, X, X, Y. Okay, yes, very good. And Dima, X, Y, X, X, Y. Okay. I just, the accept state is which one, Dima?
It is X.
X.
Because we have X to lambda. Oh, no, we don't.
No.
I have the wrong. Yeah, I see.
Cesar. Okay, it's okay, Cesar. Very good. Oksana. Okay, yes, much better. Okay, now I think everyone is ready. Okay, now I want you to observe the following. Whenever we have a grammar which says, for example, x l l lambda, or even this one, l m p p q l, something like this. Given this grammar, it is possible so that it doesn't have any lambda rules. So far, we have been looking for this format because this format is easier for us to convert into a DFA. However, now we want to prove a theorem that says that given a grammar that has lambda rules, it is always possible to rewrite it so that it doesn't have this kind of rules. So the way of converting any grammar with almost any grammar with lambda rules is the following: is whenever we have a lambda rule, such as that one, we need to rewrite all those rules that use it. For example, XL or X. But in this case, we don't disappear this one. We keep it. So we just add a new rule, assuming that L was converted to lambda. Only at the right side. Here, we just rewrite this one. Of course, we cannot disappear this L because we cannot disappear anything at the left side. And finally, we have P. And again, we have to write both versions of P, the one with L and the one without L, assuming it can go for lambda. Now, let's see if this produces the same exactly the same language. In the first one, we have S, X, L. L is an accept state, and then with an M, we have some P, and then from P, we have Q, and Q goes to L. And that's it, right? Is it correct?
Yes, it is.
Okay. Now, try to obtain the DFA from the second one, and it should be the same. Please try with the method you already know.
Teacher, a question. So with the method we know,
Yes.
we will have to add an L to the single X and Q.
Okay, but it needs to be different because in this grammar, L is already used. So remember that any
Okay.
you add should not interfere.
Okay. Thank you.
Cesar, so it says LMP PQ and SQ. I think you cannot directly reach Q from S. So please verify the state Q. There is something strange with the Q because you are not allowing the loop. So please check it, Cesar. Maraya, es, X, L, XQ, L, MQ. Okay, PQ. Okay, L, MQ. Okay, let me copy Mariah. That Cesar did, so maybe the grammar is wrong, maybe. Q, P, M, Q, Q. Okay, thank you. Okay. Okay, X. Okay, I think, Maraya, that what you did is this L to Q. There is no way of connecting L with Q from this grammar. Actually, what you have is the X connects you to this last one, not from L, but from X. Should be direct. And I think Cesar did this directly to Q, but not from L. It depends on how you converted it, but I think it's not that you need to check that. Let me check it as well. Yes, I think the grammar is correct. So just the conversion, please check it. And maybe Cesar was right. I don't know if Cesar is here.
Yes, I am, but I am reading right.
Okay, can you show me again your...
Just a moment, please.
Yes, don't worry. On the meanwhile, I check Christian. Yes, okay. Yes, Christian, that's correct. Oscar, yes, I'm trying to see, but it's too dark. But okay, yes. So the newly added state is A. Christian, yes, okay, yes, right. It's okay.
But I have a question. The data options. So I create two lambda states because if we have one lambda state, the diagram is not deterministic.
Ah, yes, don't worry. It will be
Or we don't care.
not for this part.
Okay.
If we ask for it to be deterministic, then we need to convert it to deterministic.
Okay.
Cesar, okay. It says X. Okay, yes, good. Yes, Cesar. Emilio, I think you are missing some loop, Emilio. So please check it. It should allow you to do that. Sarah, you have your hand raised. Yes, that correct. The diagram corresponds to the previous one. Most of you are obtaining something like, let me erase this one. Most of you are obtaining something like this. Like this, right? So is this equivalent to this one.
It is, but it's not deterministic. So there are like two options in node P and in node S for the same letters. So
Yes, here, for example, right? So my mistake is here is Q, right? Yes, so it's not deterministic because we have here X, and also we have here Q and Q. So it was the similar question that Camilo was asking us before. Don't worry, it can give you, this method yields you a non-deterministic finite automaton. And as you can see as well, grammars are usually non-deterministic. They don't need to be deterministic. And also, we know that we can always convert this to a deterministic automaton. So don't worry. If needed, we can do that. Sarah, you have your hand raised. I don't know if you want to ask something. No? Okay, thank you. Okay, so we are over time. I have two news for you. The bad news and good news. Which one do you want first? The good news is that there's no homework for this time. The bad news is that we have finished the chapter 1, so we need to apply an exam next Thursday. However, it's not very bad news because you already know what to do, how to solve it. Let me quickly read you. Sorry to take a little bit of your time, but I want you to know what will come in the exam. Questions are, for example, which one of the following regular expressions correspond to the following automaton? And there's a diagram, not so complex, about four states. And for this, maybe you don't need to apply the whole Ken-Thompson algorithm. You can try to solve it by following each one of the regular expressions and seeing if each one of them corresponds to the automaton. Question number 2, which one of the following automata accept the following language? It can be more than one. There is one language, and then you need to choose which diagram corresponds to it. All diagrams are only of 3 states, so the language is not so complex as well.